Hi guys, nice to see you again. This week we're gonna be reading a paper, Google USM, Scaling Automatic Speech Recognition Beyond 100 Languages. The reason I'm reading this paper was because last 2 weeks ago I was at the ICAST conference. People over there are obsessed with solving the low resource or under resourced language speech recognition problems by leveraging the scaling law. Um, this paper was published last year, but it does have a very good accuracy of on different languages compared to Whisper, and it uses unsupervised learning, uh, self-supervised learning, and also it only uses 1/10 of the size that used for the Whisper model of the label data in their ASR training, and the model exhibit a way better result than the Whisper model. So I think it's worthwhile to take a look at what these Google researchers have done and what's the implication we can get from this paper. Even we're probably not be able to fully replicate what they were doing because they leveraged lots of data resources and computational resources and human resources. And I think it's important to stress this first. These people's long-term goal is to train just one model, universal ASR model that covers all the spoken languages in the world. It's a very ambitious goal. I would have to say, even they themselves would admit that they're still not there yet, but it seems that to everybody that the result is very promising. In the past, I think for the under-resourced language, the results is not even close, but now they're getting reasonable results nowadays. It's conventional supervising approach. Yes, and this is important. With conventional supervisor training approaches, audio data needs to be manually transcribed, which is lengthy and expensive. I have to mention that we are a data service provider different than the traditional data providers who mainly manually transcribe the audio data. We heavily leverage the AI technologies, not to only to basically transcribe the data and infer the data transcription from the metadata, so it can reduce the cost of labeling data, and also it can reduce the amount of time to deliver data, which address the problem that mentioned by these speech researchers. Yes, for tail languages, everything is difficult. And this is interesting. I think I didn't fully understand their sentence. While transcribing speech may be scarce in many languages, untranscribed speech and text are practically unlimited. Yeah, this is another thing we're doing, data collection. Well, traditionally, a traditional data vendor would have to schedule people coming to their studio, either ask the people to read the prompts or give them a topic to talk. That's lengthy and expensive, and sometimes they may not be able to find a suitable person because for some scarce language or under-resourced language, you may not be able to find a person who can speak that English well. But we are heavily leverage the publicly available data, and so we can have our own way to find the exact data on the internet and deliver the right data to you. That data collection method or procedure is fast and is cost effective. This is also, I think, mentioned by the Google researchers. All these data are practically unlimited. all you have to do is to search them and filter them and clean them and deliver them. Okay. And maybe some post-processing them and transform the data into the style that you're looking for. Okay, let's go back to the paper. The recent development, they're talking about semi-supervised algorithms. They are mentioning about the Google's work. One thing is called Big SSL. I read that paper a few years ago. You can search the name in my channel at OLED Wave. Don't forget it. This is not self-supervised algorithm. This is semi-supervised algorithm. And lately, a single large model can leverage large dataset more effective than smaller model. They're talking about Whisper. I also have a paper reading of Whisper. Okay. Let's look at their approach. Okay. I think everybody put the most important thing first. You can see in this paper, different than other papers, they put their data ahead of almost everything, okay, except the abstract. Let's look at their data. First, the data can have three categories. First is unpaired audio. Second is unpaired text. Third is paired ASR data. The third one is easy to understand. You have audio and you have transcription, right? And the second is also easy to understand. It's the data that you use to train the large language models, just the text. The first is called unpaired audio, which means everything is unlabeled. And what is interesting is they're capable of getting 12 million hours of data. I think it's only Google or some really well-funded institute can afford to collect that amount of data and have the corresponding computational resources to handle this. And that's over 300 languages from YouTube. Yes, okay, Google is using YouTube. And also, this is public data. You can definitely get these public data. I think they have lots of data collection efforts. People like you and me, or people who are not working in the data industry or service industry, you may not be able to gather that many of public data in a short time. This still covers 51 languages. Although they're public, it's not easy to collect and process them in a unified format for your training. Okay, you need somebody to help you with the data cleaning and the data labeling too. Probably not data labeling, it's data cleaning. Okay, well, this is beyond my understanding. This is a large multilingual text-only database spanning over 1140 languages. Wow. And for the paired ASR test, they also have their YouTube version and the public version. Okay, public part. For the YouTube one, they have about 100 hours of labeled. This time is labeled. Multilingual data covers 74 languages. But that's lots of cost, I would say. And they also 100 hours of English pseudo-labeled data generated by the noisy student training. These noisy student training, I think, was firstly mentioned in the Big SSL. The basic idea of the noisy student training, I think, is noisy student training. I think they mentioned that in the following section of the paper. Okay, I think I will come to there when I get there. The basic idea of the noisy training is very simple. It uses first to train a unsupervised model, then fine-tune with the downstreaming task, then using the fine-tuned model to pseudo label the unlabeled data. That's basically the idea of it. It's called semi-supervised training, or you can call that. This is public data. This only have about 10 hours of labeled multi-domain English public data and 10 hours of labeled multilingual public data covering 102 languages. So this is English and this is multilingual, okay? So let me make a summary here. Altogether, this is about 12.5 million hours of unlabeled data. And this is unlabeled audio, okay? Unlabeled audio. And this is unpaired text. Text is always unlabeled, okay? This text is about 28 billion sentences, not tokens, okay? If you talk about token, let's say if there are at least 10 tokens or 15 tokens in that, I think this is about 500 billion tokens, if I'm right. That range, okay. It's less than people use to train the GPT model, I think, because most time people train GPT, they train with trillions of tokens. Now, this is only like 0.5 trillion tokens, if I'm right. And also, they have the paired ASR data. It's have in total they have 100K hours of English only, and another 100K hours of no. They have 90K hours of multilingual data. So 100K hours of English, but the pseudo labeled. And then they have, I can put this here. Altogether is 100K hours of multi-domain. Okay. Something like this, about this. Okay. And then, they talk about their encoder. The encoder is a conformer, 2 billion parameters. They're trained basically using the following steps. I will explain that in the following part. So I think you want to have to explain what the model architecture they're using. You probably want to see this. For those of you who are not familiar, what is the BestRQ? BestRQ stands for BERT-based speech pre-training with random projection quantizer. Let me give you a very rough explanation of what it is. You can check my channel. I think I have the Wave2Vec 2.0 paper reading. And BestRQ is the same as Wave2Vec 2.0, the self-supervised learning method, except one thing, the projection matrix. Did they draw the projection matrix? Yes, right here. So everything is the same as Wave2Vec 2.0, except this projection, after it's being randomly initialized, the parameters are frozen. So remember in the Wave2Vec training, this projection matrix can be updated So you can see that after this, every speech comes into it, it's like a signal processing, or just everything is fixed or frozen. So during training, the code book never changes. And also, you can see this is also frozen, right? And the code of a speech never changes. So this makes it kind of similar, also similar to the Hubert. Of course, Hubert used CE loss. This one, they're still using the contrastive loss. But the same thing of the best RQ with Hubert is that in Hubert, during training, before the next iteration, the codes of the speech does not change. All you have to do is just update the ASR encoder's parameter, not the what do you call that? The projection and the code book. Of course, Hubert would update the code book in the next epoch or iteration. What's the called iteration? Probably next epoch. I mentioned the Hubert iteration means I meant after a few epochs, they would probably want to update their code book. Okay, I do have also another have a paper reading on Hubert 2. Okay, so you can see my channel is a repository of large speech model algorithms. Okay. So after we explain what is best RQ, you can see it finished the training, get a conformer encoder. It performs the unsupervised training with the unsupervised audio. Okay. So then you come up with what? They call that USM model. And then the next step is they perform the multi-objective supervisor pre-training. They call it the MOST, right? MOST. The difference between the basic USM and the MOST plus best RQ is that after you finish the encoder, besides training with the best RQ method, they had this extra text injection by using two types of data. The first is supervised data from different languages, and also unsupervised text data from different languages. These paper, the details of the best RQ is shown here. Although this might look like a little bit very abstracted to you, but I believe that I can try to explain what it does to you. This part is best RQ, okay? Best RQ per training. Once you have the paired input, okay, it means the paired ASR input. You have the audio, you have the text. So you have the two parallel encoder. One is the speech encoder. It has the speech embedding. The other one is your text encoder. Then you have your text embedding. But the different thing of the text embedding compared to traditional BERT style encoder is that they have a resampler and a refiner blocks empowered by their duration model. And they also, after this one, they have a shared encoder, and they have a text encoder. Actually, this can be a R&T decoder, I think, because they mentioned that they use R&T reconstruction loss. And there are two things different. First is that they have the modality matching loss. The reason I think they have this is because they want to use the speech embedding to help with the training of their text encoder, especially the resampler and refiner part. Because lots of time, if you look at the duration or the length of the speech embedding, it has more samples than the text, right? Because speech is signal, text is token. You usually have more frames or samples than the tokens, number of tokens in the text. Then you have to here the method they were talking about is they just I think, let me go to the original paper of the most. I think initially they called it Mastro match speech text representation through modality matching, published about 1.5 years ago. This is what they're talking about. You can see this is the same architecture. Okay, it doesn't change. They use the resampler and refiner layers to replicate the initially learned text embeddings to match the duration of the speech embedding using this alignment information and the mean square error training objective given in the equation below. Okay, so you can see the MSE loss. You can see if you have to compare MSE loss, the two sequences should have roughly the same length, right? You can see this is the speech CS, and this is the embedding of the text. Okay, makes sense? And the thing is that you're trying to resample the resampler's input is CT, right? And then besides the resamplers, you also have a alignment, text alignment input, which comes from the R&D alignment. Okay, it means how do I say this? Well, it seems to me that this is yes, this is what exactly means. The alignment results of the R&T. And then you use these two input to get what your resampled output is. Then you also put a refiner there. I don't think they put details of refiner there. But we can see, generally speaking, during the paired input, these refiner and resamplers got updated, and also you train your text encoder compared to the best RQ. Best RQ, you don't have a decoder, right? It's just an encoder. So then on the third step, or on the third part of the input, which is text input, then you can just use the duration model. And I think at this stage, the biggest they want to see, this is the key. They want to update the shared encoder, because I don't think they would change the text encoder, especially duration model, much, because you don't have duration information. It's better not to change the duration model. And the key thing I think here is training the shared encoder. So the shared encoder can benefit from the large amount of text from different languages. Okay, this is how they inject much larger amount of text data into this ASR model. That's the Google's approach. Okay. Yes, the text. I finished the text injection part. Then they talk about the downstreaming task. So in the later on, they mentioned about their fine tuning on Fleur task, convolved task, ASR, and the automatically speech translation tasks for different languages. They're just doing everything that we do. It's the fine tuning, but they're tricky to pick up what transducer you should use. Generally speaking, the conclusion is that the short form and the speech translation, you should listen, attend, and spell last transducer or decoder. If it is a long form, they prefer to use the CTC-based decoder. If it's a low resource, they prefer to use R&D. Okay. I think you also want to see the table 1. This is why you see if the USM, so everything, all the 4 models, they use the best RQ. Okay, best RQ is a basic configuration. It trained from these 12.5 million hours of data or 10 million hours of data. And only the USM means most. Okay, use the text injection. Okay, and don't forget this. Both of these 2 models, they are pre-trained model. I personally have a different opinion because if you train the like they say mentioned in this most text injection, they already have this R&T decoder. It's ASR model. I don't think they should put pre-trained here. How to say that? Probably they meant that, okay, after they finish USM model, they would throw away the text encoder and they can still initialize the decoder while facing a downstreaming task. Probably that's what they meant. But the USM, LS, and CTC, they don't use the text injection. Their ASR models, the decoders are either LS decoder or CTC decoder. The data set they're using, it's because this is ASR, right? They use some supervisor trained model. And they use some label data or pseudo label data for their fine tuning. Okay. Here they talk about the upstream ASR data. That means it's not the final downstreaming ASR task. So they're still using some paired data as the upstream data to tune their encoder and decoder before they tune on the downstreaming tasks. Okay. And lastly, talk about their Google's signature chunk-wise attention. They have to use this because it's reduced the hallucination according to what they said. On the standard whisper model, they don't use chunk-wise attention. Talk about figure 2. This one is just saying that for the speech translation, they're better than the whisper. For the downstreaming task, they're also better than the whisper. Downstreaming ASR task. And also this is about the performance on multiple languages. You can see, especially for the Blur 112 languages, they're way better than whisper. And on the YouTube task, they're way better than the whisper. And on the English, they're better than the whisper too. Okay. Right. This is what I've just mentioned. USML, you can regard that as a pre-trained model. You throw away the decoder. That is a chunk-wise attention. I think the Google guys, they're repeating what they said. So I'm going to skip a lot of the parts here. Here they talk about their conformer architecture, but I don't think they put ablation study of the conformer size here. So I will skip this. I mentioned the best RQ already. Multi-soft max. Yeah, here they already mentioned in their best RQ paper. It's spelled, other than using a single notebook, they're using multiple code books. Right, means the multiple code books, more computational resources. Okay. Noisy student training, yes, I mentioned that. Semi-supervised learning. And also, they have something fun, interesting. They have a interesting heuristic filter to filter the pseudo-label data. 2.4, chunk-wise attention, long-form ASR. I just want to mention the key thing to you. I mean, if you look at the receptive field of a local self-attention, you will see that the deeper the network is, the larger receptive field it is. Okay. So when you train your model on relatively short sentences, then you would see that your receptive field is relatively short. Okay. But when you are applying your model on these long form, for example, YouTube interview or conversation scenario, they have a very, very long recording. Then you see the receptive field case is kind of mismatched, okay? Or how to say this? Because of the reason of the receptive field, okay? In the training, you see much constrained receptive field, but while in the long form audio, your receptive field can expand very, very wide due to the depths of your network and also the duration of the recording. Then the model is get confused, or model is tends to according to the empirical observation, under this mismatch, these models with deep architecture and high capacity suffer from high deletion errors, right? They tend to say, okay, I'm still facing I still should make a estimation or recognition results, which is short in the amount of text tokens, okay? Although they met longer utterances. So people ask, why can't you just throw long audios into the training? Right, that's a feasible solution, but you would be suffering from out of memory errors because most of the GPU's memory is limited. People want more samples in the batch, other just one very, very long audio sample in the batch, okay? That's something that limited by the hardware and cause this type of a long-form performance degradation problem. So the Google people, I think they mentioned that, but at least 4 years ago, chunk-wise self-attention. And some people, they correct me wrong. I think some people also mentioned the Mocha, right? Is it done by Google? Mocha. I might have this paper reading or not. But you can just search the Mocha. It's monotonic, chunk-wise attention, something like this. But this chunk-wise self-attention is not just done by Google people, but I've seen people from Microsoft that publish works on this. The key idea is that you see, for this one, it expands the attention. It no longer can be expand to beyond this dotted line. So it has to go this way and this way, right? And also it only can append its attention in its own receptive field. So it's like a chunk-wise, right? This is how their chunk-wise came from. And by doing this, they put constraints on their model, but the benefit is they're capable of removing the training and test mismatch, especially for the receptive field mismatch case. That's the key idea of it. And they're saying that, okay, they also talk about the issue of the whisper. I'd like to mention that. So whisper, they always segment audio into 30-second chunk and use a heuristic process to carry decoder state over. So you can see, if you give the whisper model a really, really long audio, they would always chunk the audio into 30 seconds chunk. So it seems to us whisper doesn't have this type of attention receptive field issue, okay? Because they always work on 30 seconds of chunks, okay? But there's still issue here. You can pause the video and think about yourself, right? Because the issue is whisper has uses a heuristic process, which is it fed the decoding results of the previous 30 seconds as a prompt into the input for the next 30 seconds of audio decoding. So you can see there's still a mismatch, because during the training, usually you probably just have 1 or 2 30 seconds chunk, or just one, right? I don't think you have multiple, okay? Just have a prompt there. But during decoding, you will keep having this loop. If you have a really, really long audio, for example, 10 minutes, you would have 20-ish prompts, consecutive prompts fed into your model. So you see there's a still kind of mismatch between the training and testing. And the whisper model can still be suffering from this hallucination. Okay. This is the talk about residual adaptation with a frozen encoder. This is very easy to understand. If you have heard of Microsoft LoRa, what they're talking about here is after you train this USM model, all they have to do is to just fine-tune put a few adapter layers in between in the blocks, and just to update the adapters, okay? They didn't explicitly mention what model they're using, but I assume that it should be R&D, okay? Because they mentioned that in the USM they use R&D. I don't think there's a reason for them not to use R&D, right? Because and they mentioned that here R&D is for low resource. If they are training adapter model, that means they do not have lots of data, so they would use the R&D as a decoder for on top of their conformer encoder. Although I did not see them explicitly mention that what type of decoder they're using. Okay, you see the researchers, they're repeating themselves again. They're talking about the data again. I will skip this, especially this. For those who are working on low resource language, you can see how much Google have spent on the effort of collecting the low resource languages. But you can see they work with the vendors. the final dataset contains about 100 languages, over 500 hours of each languages each. And they have a wide spread of languages. Interesting thing is that Asia, South and Southeast Asia, and Africa and East Africa, they are relatively low resource languages. Okay. All right. For the text data, they use a web product corpus. You can see where they come from. Okay. For the task, speech2 is a combination of public speech corpora, but they're not free. Okay, this public doesn't mean free. Okay, public licensed speech corpora. Some of the free, some are not free. For example, Switchboard and Fisher are not free. And the Fluors is a read speech recognition task of multiple languages. Okay. For some of the languages, you have to report the CER. And also they talk about the speech translation, COBOL. I would say this using the larger model for speech translation is very primitive as of now. So for their task, they have multilingual long-form ASR, multi-domain English US, that's speech2. Multilingual ASR, that's Fluors, and also AST as COBOL. For the multilingual long-form ASR, they have a YouTube and a Coral. Okay. And they compare the results with Whisper. Here, when they're talking about their single model, that means no fine-tuning has been done, just one model. And also their prior work. I have read this, Big SSL. For people who are interested, you should read Mastro model yourself. And this is their work in domain fine-tuning. I think this is USM. USM is just an encoder model. I believe this is plus the R&D decoder, fine-tune the decoder. Don't forget they're doing fine-tune here, okay? This is why you can see for the speech2, they can get much better result than the models that are not fine-tuned. So this, I would say that for in-domain task, nowadays, even you using large models, fine-tuning is still necessary. And for the multilingual ASR, I would say fine-tuning seems not very necessary. Okay, because you can see the LLS can get fairly good results. And the USMM with text injection, you get about 10% relatively better, right? But I would say that the general model that is not fine-tuned is good enough. And also, if you use just a frozen encoder and a train adapter on top of USMM adapter, that means you can do better than USM, but worse than the fine-tuned USM. Okay. I have to say those results are fairly impressive, especially for Fluor task. I would say that for speech2, people can achieve 7 point something easily, you know, just by training with the speech2 data itself. But for the multilingual ASR, I think this is very impressive. People are getting, for example, for the 62 languages, the average ASR is approaching 10%, which is very impressive. here they're talking about the key result, and they also show their concerns regarding the Whisper model. I think lots of us have also observed that Whisper has this very severe hallucination issues. Sometimes the WER can exceed 100%. And in terms of the long form out of domain speech recognition, they're saying that the USM CTC and the USM LLS outperform a Whisper by a significant amount. And they're saying that a USM LLS is good for short form, and they're also saying USM CTC is good for long form. Well, this is they're using chunk-wise attention, but the LLS is still not as good as USM CTC in long form ASR task. You can see the results here, right? That means the chunk-wise attention may give the model some extra constraint and hurt the model's performance. Although if it's an LLS model without chunk-wise attention, the result could be even worse. So there are lots of things that have to be done for the long form ASR task. Yeah, and I'm saying this is impressive. This is getting about 10% WER on average. Most and this is also very big too. They're multi-objective supervisor training. They can provide robust representation. And by using these, they can easily train adapter to handle the downstreaming tasks for different languages, for multilingual tasks. And also, this is for the ASR for the unseen languages. So that means in the text, you have seen this language. But for the ASR or the paired data, you have never seen these languages. You probably have seen those data in the unlabeled audio data, okay? But they're saying that compared to Whisper 2, version 2, they're doing much. They have seen these. They should have seen. They have seen this audio. They have seen these audios. Unlabeled audio, yes. Paired ASR data, no. Text, yes. Probably yes. Probably. Should be yes, right? If they haven't seen the text, how did they recognize the output, right? I think I would remove the probably here. Text. So if they use the USM LLS plus adapter, and suppose they're using, this means what? Or they just train them with the fluor data. Okay. Like this thing. That's the first step. That's step number 1. And then you train this model, then you run the semi-supervised learning by using the model trained in this step, and you get the transcription of these unlabeled data. And then you use these pseudo-labeled data you got from the first step and train this second step USM model. And you can see that you obtain the relative improvement, which are fairly significant among different languages. Okay. and they're doing very strong in the speech translation. They run some. Oh, they do have Adaptation study. Here they're talking about if you raise the size of the model, that makes sense, right? Encoders, if you get, it seems to me that this improvement is very significant. It's like a 15% important. WR dropped by 15%. So you have to use at least 2 billion parameters of encoder. Okay, this is important. And then once you have this, then you can try, if you want to have more data. YouTube 55 is how much data are there? Let me take a quick look. This is still 12 million hours. Oh, I see. So YouTube NTLU is composed of 2 parts. And this 55 rich resource languages. But if you add another 513 tail languages, that will be the full database. So let's go back to here. So that means you add another you have more data. But I would say this improvement is not that significant compared to that one, right? But it's still very big. It's still significant, very significant. And once you shift up to multiple softmax or multiple code books, and this, and then you would see that you have another significant improvement. And also they're saying that this is more stable, okay? Right. Because they use multiple notebooks, they don't suffer from codebook collapse. Chunk-wise attention, I have mentioned this. Okay, this is they are trying to demonstrate their conclusion or their argument. When you have more layers, you have bigger receptive field, you have a bigger mismatch, then you can see your WR went up, right? And also chunk-wise attention works. So this one is for the chunk-wise attention, and then this is just no chunk-wise attention, and you can see this is constantly better. Figure 7. What did you mention about figure 7? Yes. Figure 7 depicted the long-form performance degradation. Okay, discussion. That's the implication we can draw from this paper. They're saying that unlabeled data is more practical to acquire for building useful ASR for tail language than weakly labeled data. Yeah, aka Whisper, right? Whisper only use weakly labeled data for training. And also they're saying that in-domain data is the best. Yeah, that's the common sense, right? Use in-domain data to fine-tune your model. Always do this. And also, they have their comparison of different transducers. That's what they are doing. All right. Thanks for being with us. We are a data service provider. Let me see. So you can see we mainly provide two types of services. The first is the data labeling. We can offer the private data cleaning and labeling. So we install our solution on your server, so you have a minimum data breach risks. And we heavily leverage the AI-powered labeling technique, so you won't have lots of human cost, and this thing is very cost-effective. And we can guarantee the accuracy by validating those results. And also, we then run the data collection. We can, according to your data need, we can customize a large-scale data sets, especially speech data sets for you. We can do the multilingual, including those low resources, for example, Indonesian, Korean, Japanese, Southeast or South Asia language, and also multimodal data sets. All right. And thank you for being with us, and I wish you to see you next week.